Professor?
Hi, Ivan. Can you hear me okay?
Yes.
Awesome. All right. So let's get rolling here. Good morning, everybody in Marcus and on the live stream. I hope you guys are having a good week. We are wrapping up the end of this term. So I sent a fairly detailed email out yesterday that has information about the optional final exam as well as current grading. So if you haven't read that, I encourage you just to read through that to make sure you understand what's sort of left for this term. So today we're going to be covering the rest of 5.3, which we started last time. We may or may not get through it all. If we don't get through it all, we'll finish it on Thursday. But you may have noticed on Moodle, there's only one mini quiz this week on Sunday, mostly because 5.3 is so long, it was unclear whether or not we'd be able to get through it all today. So there's just one mini quiz on Sunday. There's no mini quiz on Wednesday this week. Other than that, there's going to be a Chapter 5 review on Thursday and Monday of next week. So I will send out a link and reminder about that on Thursday morning. So that's sort of what's coming up. And then next week we have our last lecture, our optional finals on May 10th. Again, the details are in that email I sent. And otherwise, we are just getting to the end. We're doing great. You guys are being awesome, and we are almost done. So let us continue our journey into 5.3. So I'm going to switch over to the dot cam here. Okay. And we started this last time. So we started talking about how we were linking up this idea of area, right, to the work that we had been doing and what we knew and what we had been assuming. And then we started talking about negative area. We talked about what that means in the context of calculus, that when you are below the x-axis, these rectangles are going to have negative area when you're talking about a definite integral. And that's when we count it as negative. We looked at an example of a negative function where we're going to get a negative answer. And then we talked about looking at a sort of generic function and determining if the area was positive or negative by looking at the values that are above and below. So when our area was above the x-axis, we said it counts as positive. And if it's below, then we're going to count it as negative. Okay. So I think we're gonna, let's bounce around for a second here. So let's talk about this example, and then we'll go back and talk about the definition because the example is sort of out of order here. So example 1, we want to find the total area between 4 minus x squared and the x-axis for this interval, right? For the interval 0 to 5. And so what I want to talk about here is the way that this is worded and how we're going to use the tools we have in sort of a non-traditional way. So we spent a lot of time last time talking about how the reason we can have negative area is because we're looking at definite integrals. And so what I want to point out here on this example is that this is not asking for a definite integral. It's asking for the area between a function and the x-axis. And so the way that this is worded is that we need to find an area like we would outside of calculus, where we're looking at how much space is taken up for this function. So I'm just going to draw a picture of what we're actually looking for. And I think that will help us start to figure out how we might do this using the tools we have. So we have this upside down parabola. It's a little off center, but you get the idea, where we are looking at what's happening between 0 and 5. So this is 2, 1, 2, 3, 4, 5. And this just goes on down, 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 down. Just keeps going down. Okay. So what we're trying to do is we're trying to find this area, which we'll call area 1. And we're also trying to find this area that would keep going down until we intersect, which we're going to call area 2. Okay. The problem is we need both of these areas to be positive because of the way this is worded. There's no definite integral stated in this problem. However, we can use definite integrals to answer this problem But in order to do that, what we need to do is we need to figure out a way to count the negative area as positive. Okay, so what we want to do is we want to set up two definite integrals, one for the positive area and one for the negative area. Once we've calculated those, we're going to take that negative area and count it as positive, since we're not talking about integrals in this particular example. So I'm going to have you try this. I'm going to give you 2 minutes. You're going to set up an integral from 0 to 2 for your function, and then another one from 2 to 5. And then again, we need to count all the area as positive to answer this particular question. Okay, so see if you can try that out, set it up, plug it into your calculator, see what you get, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, the reason we need to split this up into two integrals is because the area above the x-axis is going to be counted as positive in your calculator, and the area below the x-axis will be counted as negative in your calculator. And we need to figure out exactly how much area is being taken up by each space before we can add them together. So here, our first integral, we have the integral from 0 to 2 of 4 minus x squared dx. When we plug that into the calculator, we need to be extra careful. Remember, you can put things in terms of x and then make sure you have that dx there because that's our operator. When we plug that in, we're going to get 5.333 repeating, okay, or 5 1/3. So that's the positive area that we get from 0 to 2. We then also want to do an integral from 2 to 5. Why to 5? Because again, we're interested in 0 to 5, and we split it at the point where we cross through the axis. So here, if we integrate from 2 to 5, if we plug that in the calculator, we get -27. Now, how come we can't just plug in 0 to 5, right? If we plugged in from 0 to 5, what would happen is that the calculator would add -27 plus 5.33, so we get like -21.666. But the way that this question is asked to find the total area between the function and the x-axis means we're looking for the positive amount of space that we take up. So that means we need to add these two numbers together in absolute value. Okay, so the 5.333 stays positive, but now negative 27 becomes positive 27. And when we add those together, we get 32.3 repeating. And so this is a very subtle shift from the types of questions we've been doing. And so it's important to notice how this is worded and how it does not involve area under the curve, right? As in it's not asking for an integral in the example. So we are using integrals to answer the generic question about area. So it's a slight difference, okay? So now that we've sort of thought about that in some sort of way, we ask the question, how do we deal with functions that are positive for some areas and negative for others? And this question is really addressing how do we deal with that in an integral, right? So this is a different question. This is about area. That's not related to calculus, just general area. So when we're talking about this in terms of an integral or area under the curve, what your calculator will do is it's going to sum up everything that's positive, that's above the x-axis. It's going to sum up everything that's negative, and then it's going to put it all together in terms of positive and negative to find out how much we actually changed. So if you have, you know, 1 unit of area that's positive and 1 unit of area that's negative, when you do that definite integral, you find that there was 0 change. Why does that make sense, right? -1 plus 1 is 0, but what does that mean in context? That means your function increased by 1 unit and then decreased by 1 unit, which means you're at the same point you started at. So there was 0 change. So it's looking at how much you increased and decreased over the entire function. Okay, so one way to think about this, let's look at an example. I think that will help us sort of visualize what's going on, okay, is by thinking about this in context, right? So in the context of some sort of example where we can see what's happening. So we have this figure below, which is a derivative, and it shows the rate of change of the value of an investment over a 5-month period. Okay, so again, this is the rate of change, so it's the derivative of an investment. And so we want to be able to use this to start interpreting what different things about this picture tell us. So part A, during which months is the investment f of t gaining value? So again, it's asking questions about the original function based on the derivative. When are we losing value? During which months is the investment at a minimum? So let's think about that, what we know about minimums in relation to the derivative. And then part D, during this 5-month period, does the investment make or lose money? So this is looking at areas and what we know about whether they're positive and negative. Okay, so I'd like you to take 2 minutes, see what you can come up with for these questions, see what you can figure out based on the picture, jot down your thoughts, and then we will go through it together. Okay, take about 30 more seconds. Okay. So let's look at each piece of this and see if we can figure out how this graph is going to help us answer our questions. So we are trying to figure out during which months is the investment gaining value. So that means that the original function should be increasing, right? Because if the original function is the investment, it's going to be gaining value when it's going up, right? So how do we use the derivative to determine where the original function is increasing? So this goes back to some of our analysis before about the relationship between the derivative and the original function. And the relationship says that when the derivative is positive, which means above the x-axis, that tells us that the original function is increasing, okay? So here, that means from time equals 3 months to time equals 5 months, the original function will be increasing. Therefore, we say it's gaining value because, again, that's where f prime of t, the derivative, is positive. During which months is the investment losing value? So again, we're looking at the derivative to talk about the original function. And the relationship is that when the derivative is negative or below the x-axis, that's when the original function is decreasing. And if the original function is decreasing, that means we are losing value over time. So that's going to happen from month 0 to month 3, because here we see that the derivative is negative or below the x-axis, okay? During which month is the investment at a minimum? Okay, so let's think about minimums for a second. So we know that minimums happen at endpoints or critical points. Here we can see that we're going to have a critical point at 3, because that's where the derivative equals 0. And our critical point changes from negative to positive, which means the original function was decreasing and then increasing. So this we know creates a minimum because of the way that it changes. So we're going to have a minimum value at 3. So if we're thinking about like what our original investment is doing, right? It's decreasing and then we turn around and we're increasing, right? So we're going downward and then we turn around. So we see that there's a minimum at that critical point. So then the last question is, during this 5-month period, did this investment make or lose money? So the question is really, is this endpoint higher or lower than where we started, right? Is there a way for us to figure that out? Well, that's where we loop in the area, right? We want to know, how does the area where we are decreasing compare to the area where we were increasing? If the area above and below are the same, that would mean that we would have 0 change. But if the area below the x-axis is greater than above, which is what we have here, that means we decreased more than we increased, which means that we are going to have lost money over that 5-month period because the negative area is greater than the positive area. If the positive area had been greater, we would have made money over that 5-month period. So we're able to sort of eyeball this area and guesstimate which one is larger in order to answer this particular question. Okay, so this is a scenario where we have positive and negative values, and this is how we are evaluating it, right? We're considering what the negative values tell us, what the positive values tell us, and what it means overall. Okay, so the next example is going to help us still keep considering what happens when you have both positive and negative values. This printed on 2 pages. I don't know why. So consider the function f of x equals x cubed minus 7x squared plus 11x. I'm just going to rewrite that up here at the top because it's much better if it's all on 1 page. So x cubed minus 7x squared plus 11x. So that's the function we're looking at here. Okay. So there's a whole lot of steps here that are going to help us understand how we sort out what is positive, what is negative, how we evaluate it and what it means in context. So what we're going to be doing is we're going to start by graphing this function from 0 to 4. So you can do that on your calculator. If you don't have a calculator, you can pull it up on your phone. You can go to like Desmos or something like that to see what this function looks like from 0 to 4. And then we need to figure out for what x values does this function cross through the x-axis. So by determining where we cross through the x-axis, it's going to help us sort of understand different points we might be able to set up to find different types of areas. So once we know where it crosses through, part B says, consider the area that is above the x-axis, set up an integral to represent the area above the x-axis. Okay, so you'll have one chunk that's above and one that's below. So we're just calculating area above. For part C, we're going to calculate the area that's just below the x-axis. So this is going to be more helpful once you have your picture. You're going to set up the integral that represents that. We're going to calculate that. For part D, we're going to use our answers to find the total area bounded by the function. So this is like the first problem we did, where this is just asking to find the general area. So we have to count positive and negative areas as positive and add them together. And then in part E, we say if capital F of x has a derivative of little f of x, which means that now we're talking about what's happening in calculus, we have a rate of change. Use your answers from part B and C to find the total change from 0 to 4. So this part D is asking for just area, but part E is saying, okay, well, now we know this is a rate of change. So what is the total change? So this is where you will add B and C together in their form. So, you know, positive will be positive, negative will be negative. So this one has a lot of steps. So I'm going to give you about 3.5 minutes to work this out. You know, see what you can do, see what you can figure out, and then we will go through it together. Okay, take about 30 more seconds. Okay, so for part A, we are trying to graph this function from 0 to 4. So when we graph it, we get something that looks like this. So it starts off increasing and then decreasing and then sort of cuts off at 4. And so for part A, we're asked to find where we cross through the x-axis. So you can either sort of trace this or calculate on your calculator. I would not recommend setting this equal to 0. I mean, you can do it and factor it, but typically it's pretty easy to do right on the calculator. And you're going to get 2.382. Okay, so that's the point where we're changing from positive area to negative area, and it's the point where we cross through the x-axis. So for part A, or for part B, sorry, part A was the graph. For part B, we're trying to find the positive area. So the positive area is where this starts, right? So this starts off with positive area. So we are looking at the integral from 0 until we get to 2.382. So that's the point where we cross the x-axis. So this is where we're going to find our positive area. So if we integrate our function between 0 and 2.382, we're going to get the positive area, which is 7.719 approximately. Okay. For part C, we are asked to find the negative area. So the negative area is going to be when we are below the x-axis. So when we set up that integral, we're going to start at 2.382, right? That's where we begin. And then we're going to go until 4. 4 was our upper bound that was given in the problem. So we integrate the function on those bounds. We get negative 5.053. Okay. So now we know how much area is above and how much is below. So the way we approach the next two questions is really based on how they're worded. So for part D, it wants you to consider this as just area under some random function between the function and the x-axis with no reference to calculus, derivatives, definite integrals, anything like that. So if we're taking area for what it's worth at face value, we're just talking about how much it takes up in space. So this is where we're going to do 7.719 plus 5.053. So we're taking the positive value of this to just talk about how much space it takes up. When we add these together, we get 12.772. For part E, however, we're told that this f of x is a derivative and that now we are interested in the total change of the original function. So that indicates that we are interested in a definite integral. And so the total change is to add these up as is. Okay, so the positive stays positive, the negative stays negative. And we get 2.67 because our original function increased by 7.719 and then decreased by 5.053. So the change is how far we are from where we started, which is 2.67. So the wording of these is just meant to help highlight when we use which technique, which can be a little tricky when you first start doing these, but you do get used to it as you go. Okay, so let's do a couple more examples where we're really considering positive and negative areas here and how they work. So suppose a person is 50 miles away from their home and is driving in their car in a straight line. Their velocity is given in the graph below. So you're already 50 miles away from home and you're driving away from your home initially. A, when is this person farthest from their home? Okay, and approximately how far away are they? So we need to think about when the position function is increasing and when it's decreasing in relation to their home. For part B, when is this person closest to their home and approximately how far away are they? And part C, how far did they travel over this 5-hour period? Explain their end position in relation to their home. So I want you to think about how we can use this graph of velocity, which is rate of change, to think about how we would answer these questions. Okay, I strongly encourage you to draw a picture. I think it will help. We can even draw the starting picture together. So we have this little house. This is the home, right? We start off and we're driving. Oh yeah. We're driving and we're 50 miles away from home, right? And this is where we start. So thinking about what the picture is going to tell us about how we're traveling, notice that the 0 axis, the t-axis is right here in the middle, which is a little bit goofy, but this is 30 and 60. Here's -30, -60. When you're traveling above the x-axis, you're moving away from your home. You're going in this direction. And when you are below the t-axis, you're going back towards the house. So I'm going to give you about 3.5 minutes to see what you can figure out here. It's a little bit tricky, but it's kind of a cool problem. I think it's a little bit clever. So see what you can figure out, and then we'll go through it together. Okay, take about 30 more seconds. Okay. Let's think about how we can stay organized when we're figuring out what's going on with this car and how to answer these questions, right? So we want to know when they're furthest from their home, when they're closest to the home, how far away are they? So we really want to figure out how to take the information from this graph and put it on our picture so we can figure out what's going on. So notice that time is in hours, and over the first 2 hours, we're moving away from the house, and that is represented by positive area. So the first thing we really want to do is we want to approximate the positive area. Okay, so we're talking about something like this. So I would say the best way to approximate this, given the shape of the graph, is just to look at it like a triangle. 1/2 base is 2 units long, height is 30. Right? So we have 30 times 2 is 60, divided by 2 is 30. So that means over the first 2 hours, we go another 30 miles away from the home. So that's 1 hour, that's 2 hours. And now the distance from home to here is 80 miles. So after that 2 hours, we are now 80 miles away from our home, okay? But then we see that our graph goes below the t-axis, which means that our car has turned around and is going back in the other direction. So now we're going back towards the house, right? So we're gonna start going sort of back towards the house, but how far do we go back in the other direction, right? So again, we're trying to approximate this area to tell us how far we went. So if we do 1/2 base times height from 2 to 5, that's 3. And now notice this one comes down further, and it's -60, right? And we know that the negative area is telling us about the direction that we're going, right? So again, when we have negative area, it helps us understand something in terms of the problem, and in this case, it's direction. So here, when we multiply these together, we're going to get -90, okay? So that means we're going 90 miles in this direction. So notice we'd only gone 80 miles in this direction and 90 miles in this direction, which means that we are now going past our house, which is here, and back this way, right? So how far did we go past the house? Well, if we had gone 80 miles this way and 90 miles this way, then at the end of this, we are 10 miles away from the house in this direction, right? So this negative means we're going back towards the house. So the first question, I think we can answer with just the information we have here. When is this person farthest from their home? So here, the 80 miles in this direction is the furthest from home because we only ended up going 10 miles in this direction, right? So the 80 miles happened after 2 hours. So at time equals 2. Okay. So at time equals 2. And they were 80 miles away. So that's how we're going to answer part A and think about this in terms of our picture. Okay. Part B asks when this person is closest to their home, right? And so we know from our picture that we are literally going to drive right past the house. So we're trying to approximate when that happens, right? So let's think about this. So from time 2 to time 3, and from time 4 to time 5, right? Those aren't quite as big, but when we're thinking about these areas, we can either approximate by doing exact areas and then trying to break up the 90 into 3 pieces, or we can assume that they're all equally likely. Either way is fine. But what I want to point out is that since we only went this far, we're probably pretty close to the 4 to 5 hour, right? We're at the end of this trip. So let's see how we might be able to approximate these to help us understand where we were, right? And this is not exact, so we may not get the same exact answer, but we should be in the same realm of somewhere between hour 4 and 5, just based on what's going on here, right? So here, right, this is like 1 unit from 2 to 3. Let's say this goes down to halfway between -30 and -60, which is -45, right? So this is 1/2 1 times -45. And let's say that this is roughly the same, right? So we have 1/2 times 1 times -45. So we have half of 45 from time 2 to 3 and from time 3 to 4. So half of 45 is 22.5, right? So that means that from here to here, so from time 2 to time 3, we are subtracting 22.5 from the 80-mile mark. Because remember, we were 80 miles when we turned around. So we'll 80 miles from home. I'm actually going to put that in another color so we can keep track of that. So we were 80 miles from home, right? And then we subtracted off half of 45, which we said was 22.5. So that's 57.5, right? Which means that this area here, if we're saying the whole thing is 90, is another 45, right? Because we said the whole thing has to add up to 90, 22.5, 22.5. This would give us 45. So from time 3 to time 4, we're going to go another 45 miles. So 57.5 minus 45 brings us within, now we're at 12.5 miles from our house. And so here we see this is the other 22.5. So right somewhere between hour 4 and hour 5, right, is what we said. So again, this is 22.5 total miles. So, you know, a little more than halfway, but right about 4.5, somewhere in there is where we're going to be right at home. I think 4.5 is a pretty reasonable approximation, right? You could do 4.3, but that's how we're thinking about all of these numbers in context and how we can approximate when this person is closest to home using these areas. So what's the base assumption here is that these little triangles here are 1/2 base times height, and I'm using this height of -45, and that's just an approximation, okay? So again, you know, anywhere between hour 4 and hour 5 is what we're aiming to get here. For part C, approximately how far did they travel over the 5-hour period? Explain their end position in relation to their home. So how far did they travel over the 5-hour period? Well, we know they traveled 30 miles in one direction for the first 2 hours. So time 0 to time 2, they went 30 miles. So this is the first leg of their trip. And then from time 2 to time 5, they went 90 miles in this direction, which means that in total, they went 120 miles is how much they drove. They drove 30 miles one way and then 90 miles the other way. The last part, explain their end position in relation to their home. Well, since they were 80 miles away from home and then 90 miles back in this direction, that means that they are now 10 miles away from their home in the other direction. Okay, so they're now 10 miles away in other direction. Okay, so they've driven right past their house and they're 10 miles away over here. Okay, so like I said, there's just sort of like a little puzzle here where you're trying to figure out how the pieces fit. We're using the graph to help us approximate and understand how to answer these questions. Again, it takes a little bit of time to sort of think about how all these pieces work together, but it's just another example of why we need to have both positive and negative area working in conjunction with one another. Okay, so now that we've sort of looked at how we deal with positive area and negative area working in conjunction together, we have to take it to the next step and say, okay, so now we know about positive area above the x-axis. We know about negative area below the x-axis. The next step is how do we talk about area between two functions, right? So no longer worrying about the x-axis, but instead thinking about area between two functions. Okay, so let's consider a picture that looks like this. I'm just going to trace this because this did not come out as dark as I wanted it to. Okay, so let's call this function f of x, and let's call the bottom function g of x. Okay, consider now if we are interested in the area between these two functions for some set of bounds. So for the sake of visual, let's say from 1 to 3. Okay, so we are interested in this area here. Okay, so area between two functions. How do we use what we know about integrals to figure out the area between two curves? Okay, so let's start with thinking about what if we integrate f of x from 1 to 3, right? So what does that look like, right? Let's call that a. So if we were to integrate f of x from 1 to 3, just the top function, it would be the area between the function and the x-axis. So it would be that area here. That's area A, right? That red area. Now let's think about the area from 1 to 3 of g of x. We'll call that area B, right? So if we were to integrate from 1 to 3, the g of x function, that's going to be this right here, right? That's B. It's this area down here. So what we notice when we do this is that if we were to subtract off this g of x area from the f of x area, what we're left with is the area we want, the area between curves. So it's not a coincidence that this sets up this way. So if we wanted to set up this particular area, right, we would have the integral from 1 to 3 of f of x minus g of x dx. Now, area under the curve is like derivatives in that you can separate them by addition and subtraction, and you would still just do the area under the first minus the area under the second, which is what we want here. So in general, if we want area between curves, we're going to have the integral from a to b, so whatever bound you're looking between. And the way that the formula works is it's written as f of x minus g of x dx. And this is a bit deceiving because a lot of the time you're not even going to have like an f and a g. You're just going to have like y equals this and y equals this, or, h and g, or, what if g was on top? So the way I want you to think about this formula is top function minus bottom function. Okay, you want the one that's on top minus the one that's on bottom, right? That's going to help us get that area that we're looking for between the two curves. Okay, so how do we use this in context? What does this look like? So there's sort of two cases that come up with area between curves. The first case is when we have bounds, right? A and B. And I know what you're thinking, how can you not have bounds? They're in the formula. So we'll talk about that when we get to it. But we're going to start by looking at examples that do have bounds to see how we set these up. So for the first example, we want to find the area between y equals x plus 5 and y equals 2x plus 1 from 0 to 2. So what I want you to do is I want you to graph these functions, or if you have the notes printed, you can look at the graph, but I want you to figure out which function is on top and which function is on bottom when we're looking at 0 to 2. Okay, then once you know which one's on top and bottom, I want you to set up an integral to find the area between the curves and then plug it into your calculator to calculate that area. Okay, so I'm going to give you 2.5 minutes, maybe 3. Try to set that up, see what you can come up with. The picture is really going to help. So if you don't have the notes printed, definitely, sketch the graph of what you think it might look like. And then we will go through it together. Okay, take about 30 more seconds. Okay. So when we sketch this out, right, we have two linear functions. We have x plus 5, which is this blue function. Ooh, pretend that that was really straight. And then we have our second function, 2x plus 1, which comes up like this. Okay. And in this particular problem, we were asked to find the area from x equals 0 to x equals 2. So 0 is here and 2 is here. So the area that we're looking for is this area between the curves, right? 0 to 2. We're not looking everywhere. We're just looking at the bounds that we were given. Now, when we set up our integral here, the 0 to 2 is what goes on the integral. And then we want to do top function minus bottom function. So we have x plus 5 minus 2x plus 1. Okay, so a couple things. You definitely need to use parentheses because when you subtract off a function, you have to subtract off all the terms. Okay, you can enter this into your calculator just like this with the parentheses. That's totally fine and you will get the answer, or you can simplify first if you prefer. Either way, you will get the same answer. Okay, when we plug this into the calculator, we're going to get the value of 6. Okay, so this area is 6. The amount of space it takes up is 6 units. And I do want to point out that the top minus bottom is important. And if we had been looking at area way over here, notice that the top function is different once we pass through the point where they are going to intersect. So it's really important that you're looking at the whole picture and knowing where things intersect and where they don't. Okay, so we're going to see this come up in the next example. So here, find the area between the curve y equals 3x and x squared. So I'm going to just trace this. From -2 to +1. Okay, so this is what the picture looks like. And we're interested in what's happening from -2 to +1. So I'd like you to think about how we might approach this, what tools we might use, and how we might need to do this to find the area between the curves. So I'm going to not say too much more about this. I'm going to let you try it out. I'm going to give you 2 minutes, see what you can figure out and set up. Yeah, let's try it out, and then we will do it together. Okay, take about 30 more seconds. Okay. So when we think about where we're interested, -2 to +1, if we were to shade this in, so -2 to +1, by having this picture, we are able to see that something is happening right here at 0, right? That the function that's on top is going to switch. And so that means we need to be careful, and we need to actually set up 2 integrals, one for each time that the function switches. Okay, so here we need to do an integral from -2 to 0. That's going to represent this first area between curves, because in this scenario, from -2 to 0, the x squared function is on the top. So we have x squared minus 3x dx. Okay, when we calculate that area, we get 8.666. So we'll round it to 8.667. So that's this area here. Okay, but at 0, we switch. And so from 0 to 1, now the 3x is on top. So we have 3x minus x squared dx. It's important that we set these up, and if they switch, we set up an integral for each separate area to make sure that it's reporting correctly. Otherwise, it's going to count this as negative if you don't switch it, right? And that'll be problematic. So here we set that up, we get 1.666, so we get 1.667, right? So we're going to add those together, right? So we have area 1 plus area 2, we get 9.834, something like that. Okay, so if we had looked at the area until 5, right, we would have to separate it again here at 3. So at 0 and at 3, so we'd have 3 integrals. So from -2 to 0, 0 to 3, and then 3 to 5. So every time it switches which one's on top, you need to set up a new integral to calculate the area. The only really way to know that it's switched is to have a sense of what the picture looks like. So that's why we're drawing the picture each and every time, so that we know, what's going on and what that looks like. Okay. So those 2 examples had bounds, like I mentioned, and I mentioned that sometimes we don't have bounds. And so what does that look like? How do we deal with that, right? What types of things are we getting at? So this is the type of question you would see where we don't have bounds. And so let me just trace this. Okay. So now this is the same 2 functions we looked at before, but now the question becomes, find the area that is naturally bounded between y equals 3x and y equals x squared. So how do we know where something is naturally bounded? We're looking for the area that is completely enclosed by the 2 functions. So in this case, the area that we're trying to find is this one. This is the only one that's enclosed. If you try to shade in an area up here, it goes on forever. Over here, it goes on forever. Over here, forever, forever, forever. There's only one spot that's completely enclosed. So this is going to add one additional step for us, where we need to determine where these 2 functions intersect, because that's going to be our bounds. So step 1 is determining where the 2 functions intersect. You may be able to do this algebraically or on the graph. Then once you have the intersection points, those are your bounds of your integral. And then you're going to do top function minus bottom function for this enclosed area. Okay, so again, there's just one extra step of finding the bounds. But other than that, we're still just doing top minus bottom, okay? So take 2 minutes, see if you can find those bounds, see if you can set that up, top minus bottom, and get that enclosed area, and then we will go through it together. Okay, take about 30 more seconds. Okay, so we need to find the intersection points, and you can do this graphically, but if you were going to do it algebraically, we would want to know where these two functions equal each other. So the way we would do the algebra on that is we'd bring the 3x over, we'd subtract it from both sides, and we'd set it equal to 0, right? So from there, we can factor out an x times x minus 3 equals 0. So we get x equals 0 and x equals 3. So that's where we're going to intersect. And if we look at our picture, we see that that makes sense at 0 and 3. That aligns with what we see happening in the picture. So again, if you set two functions equal to each other, you can find where they intersect. So those become our bounds. So we have 0 to 3. And now we want to do top function, which is the linear function, minus bottom function. Okay, so we have 3x minus x squared. We plug that into the calculator, and we get that this little area that's enclosed naturally is 4.5. So again, if you have a situation where you're not given bounds, you're looking for the place that's naturally bounded. So you find those intersection points, and then you proceed with the same process as before. Okay, so we're going to stop there. We'll start with example 7 next class. Again, your mini quiz is not till Sunday, just because this particular section is very long. So try some of the homework on 5.3 to get you kicked off. We'll do this last example on Thursday, and then cover 5.4. Okay, have a great rest of your day, and I will see you all on Thursday.